Thank you for the introduction. Today, I will discuss the multi-party consumption discrimination, focusing on the factorizability of optimal discrimination of the LCC, that is the local operation and relational communication. This is the joint work with my postdoc mentor, Professor Jong Kim. This is the outline of my talk. First, I'm going to talk about multi-party quantum state discrimination and review the definition and property about the error discrimination, optimal error discrimination, and optimal separable discrimination. Second, I will discuss multi-party quantum discrimination and present our result on the factorizability of optimal LCC discrimination. And finally, I will summarize. While the previous talk focused the two-party quantum state and measurement, in this talk focus multi-party quantum state and measurement. I will also introduce several sets. H denotes the set of Hermitian operator, and H plus denotes the set of positive semi-definite operator. Hence, multi-party quantum state is described by an element of H plus with unit trace. Measurement is described by a subset of H plus satisfied its completeness condition. Moreover, we use set to denote the set of separable operator in H plus. In other words, set is the set of all positive semi-definite operator and can be written as the sum of positive semi-definite product operator. Additionally, we use set star to denote the set of set. An element of set is also called the block positive because its inner product for any product vector is always non-negative. In particular, a block positive operator that is not positive semi-definite is called an entanglement witness because its inner product is not negative for any separable state, but negative for some entangled state. This diagram represents the inclusion relation among the sets H plus, then F star. This shaded region is the set of entangled witness. So I will discuss multi-party quantum state discrimination. So let's think about the situation of discriminating multi-party quantum state rho I, where the state rho I is prepared with the probability eta I. We describe this situation by the ensemble epsilon consisting of the state rho I and the corresponding probability eta I. Here, N is the set of all integers from 1 to 4n. In this situation, we use a measurement M consisting of Mi. For each I, obtain the measurement outcome Mi means that we get the prepared state to be rho I. When the state rho I is prepared, the probability of obtaining the measurement outcome Mj is given by trace rho I Mj. So the average success probability is given by sum over I of eta I trace rho I Mi. The minimum error discrimination, the ensemble epsilon, is to maximize the average success probability of possible measurement. We denote the maximum success probability by PG epsilon. We can also think about the restriction on the measurement. When the available measurements are limited to LHC measurement, we denote the maximum success probability by PL epsilon. Here, an LHC measurement is a measurement that can be implemented using local operation by each of the n parties together with classical communication. Similarly, we denote by P set epsilon the maximum success probability of possible separable measurement. Here, a separable measurement is a measurement consisting of separable operators. From the definition, we obtain this relation. The first inequality is obvious. The second inequality holds because every LHC measurement is a separable measurement. And the last inequality is satisfied because simply guessing the most probable state is an LHC measurement. Now, I will explain when one of these inequality become an equality. Proportion 1 provides a necessary and sufficient condition under which the first inequality becomes an equality. In other words, the minimum error discrimination of a quantum state ensemble can be realized using only separable measurement. If and only there exists a separable measurement and a Hermitian operator satisfy this condition. Proposition 2 provides a necessary and sufficient condition under which the second inequality becomes an equality. In other words, the optimal separable discrimination of a quantum state ensemble can be realized using only LHC measurement if and only there exists an LHC measurement and a Hermitian operator satisfy this condition. The difference with proportion 1 is that separable measurement is replaced by LHC measurement and H plus is replaced by delta. Our result shall 1 establish a necessary and sufficient condition under which the last inequality becomes on equality. In other words, the optimal LHC discrimination can be realized just by guessing the most probable state, if and only if this below positive condition is satisfied. From here on, we obtain the following corollary 1. Corollary 1 shows that the optimal LHC discrimination of quantum state ensemble leads to the sterilization. If and only if all the probability eta i's are equal to 1 over n, and all the state rho i's are identical. So let us talk about the proof of corollary 1. First, assuming that this equation is satisfied, this means that the optimal LHC discrimination of the ensemble epsilon leads to just random guessing. In this case, we obtain this relation. In this relation, these inequalities are obvious, and the equality is from this assumption. This relation means that all the probability eta i's are less than or equal to 1 over n. Since the average of the probability eta is 1 over n, or the probability eta i's are equal to 1 over n. This equality is from this equation, and the inclusion is from this equation and this equation. Because P and epsilon is equal to eta 1. Since trace this block positive operator is the zero operator, it follows from this equation that this equation is satisfied. That is mean all the state I are identical. Conversely, suppose that all the probability eta i's are equal to 1 over n, and all the states rho i's are identical. In this case, this relation is obvious. Thus, here 1, our result leads to us that this equation, which completes the proof. We also note that the necessary and sufficient condition for PG epsilon to be 1 over n is the same as that for PR epsilon to be 1 over n. So there is no ensemble satisfied this relation. The strict inequality means that the minimal error discrimination of the ensemble epsilon performs better than random guessing, and the equality means that the optimal error discrimination of the ensemble is equivalent to random guessing. Now, I'm going to talk about multi-party quantum sequence discrimination and present our result, the factorizability of optimal error discrimination. So let's think about the situation of quantum sequence, where each quantum sequence is a sequence of multi-quantum states from the ensemble epsilon 1 through epsilon large n. This figure illustrates the process of preparing a quantum sequence and sharing it to the n party, A1 through An. Initially, the state rho C11 is prepared from the ensemble epsilon 1 with the corresponding probability eta C11. At each step small l, range from 2 to large L, the state rho C small l is prepared from the ensemble epsilon small l with the corresponding probability eta C small l. As a result, the quantum sequence rho vector C is prepared with the corresponding probability eta vector C. The quantum sequence rho vector C is the tensor product of rho C LL over steps L, ranging from 1 to large L. The corresponding probability eta C vector C is the product of the probabilities eta C LL over steps L ranging from 1 to large L. We describe this situation by this tensor productive ensemble consisting of the quantum sequence rho vector C and the corresponding probability eta vector C. Here, n vector n is the Cartesian product nn1 through nn large L. nn1 is nn small l is the set of origin from 1 to small n small l. In this situation, we use a measurement M consisting of M vector C. For each vector C, obtain the measurement outcome M vector C means that we get the prepared quantum sequence to the rho vector C. So the average success probability is the sum over vector C of delta vector C trace, rho vector C, and vector C. The minimum error discrimination of a quantum sequence ensemble is to maximize the average success probability of all possible measurement. Similar to state discrimination, we denote the maximum success probability by PG, this tensor productive ensemble. We can also think about some restriction on the measurement when the available measurement are limited to LC measurement. We denote by PR epsilon the maximum success probability. Similarly, we denote by P step this tensor productive ensemble the maximum success probability of all possible separable measurement. Similar to state discrimination, is followed from the definition that we obtain this relation. Now, let's think about the situation where a measurement is performed at each step of the quantum sequence. The following figure illustrates this situation. This is equivalent to performing the measurement consisting of this tensor positive operator. In this case, we obtain this relation. This means that the average success probability of this tensor product ensemble can be written as the product the average success probability at each step L. From this relation, we obtain this inequality. This means that the minimum error discrimination of a quantum sequence ensemble is no worse than performing a measurement at each step of the sequence. Due to similar reason, we obtain this relation. This means that the optimal error discrimination of a quantum sequence ensemble is no worse than performing an error measurement at each step of the quantum sequence. Recently, the following proposition was shown. Proposition 4 shows that the minimum error discrimination of a quantum sequence ensemble can be factorized into that of each individual ensemble. This naturally raises the question of whether the optimal error discrimination of a quantum sequence ensemble can also be factorized into that of each individual ensemble. To answer this question, we now discuss the factorizability of optimal error discrimination. First, we say that the optimal error discrimination of a quantum sequence ensemble is factorizable if this equality is satisfied. This means that the optimal error discrimination of a quantum sequence ensemble can be factorized into that of each individual ensemble. With this relation, we establish now. With the relation, we establish sufficient condition under which the optimal error discrimination of a quantum sequence ensemble is factorizable. Theorem 2 provide a necessary and sufficient condition under which these highlighted inequalities become inequalities, and the factorizability of optimal error discrimination holds. This result implies that the optimal error discrimination of quantum sequence ensemble is factorizable if the minimal error discrimination of each individual ensemble can be realized using only error measurement. So let's talk about the proof of theorem 2. First, suppose this equality is satisfied. This means that the minimal error discrimination of a quantum sequence ensemble can be realized by RCC. In this case, these equalities are satisfied because otherwise this relation is false. The first equality hold is from this position, and the second equality is from the factorizability of minimal error discrimination. The third inequality holds because one of these equalities fails. So conversely, assume that these equalities are satisfied. This means that the minimal error discrimination of each individual ensemble can be realized with only RCC. In this case, we have this relation. These inequalities are obvious. The first equality is from this equality. And the second equalities are from the factorizability of minimal error discrimination. Since the first and last term in these relations are the same, we have this equation, which completes the proof. Theorem 3 provides a necessary and sufficient condition under which the last inequality becomes an equality. In this case, the optimal RCC discrimination of a quantum sequence ensemble can be realized simply guessing the most probable quantum sequence. And the optimal RCC discrimination of this test probability ensemble is factorizable. The statement of theorem 3 follows directly from theorem 1. So let's talk about the proof of the second statement of theorem 3. First, assume that this equation is satisfied, means that the optimal RCC discrimination of a quantum sequence ensemble can be realized just by guessing the most probable quantum just by guessing the quantum sequence rho delta x. In this case, we can have this relation. Since the first equality is from this position and the rest are obvious. Since the first and last term in these relations are the same, we have this relation because all inequalities are equalities. Thus, in this case, the optimal RCC discrimination of this test probability ensemble is factorizable. Theorem 4 provide a necessary and sufficient condition under which the second inequality becomes an equality, and the factorizability of optimal adversity discrimination holds. This result implies that the optimal adversity discrimination of this tensor-positive ensemble is factorizable if there is adversity measurement and a Hermitian operator satisfying this condition. Shear 4 follows from proportional 2, but in this talk we omit the detailed proof. Now let us consider some examples to illustrate our result. Example 1 shows that the optimal average destination of a quantum sequence ensemble is factorizable not only in trivial case but also in non-trivial ones. In this case, in this example, from our result, we can obtain this relation. These equalities are from theorem 4. Theorem 4 means that theorem 4 is a necessary and sufficient condition under which these equalities are satisfied and satisfied. And this 3-3 inequality is from theorem 2, and last street inequality is from theorem 3. From this relation, the factorizability of optimal average discrimination is possible even if this relation is satisfied. First inequality means that the minimal error discrimination of a tensor product ensemble cannot be realized using LCC. The second inequality means that the optimal average destination is tensor product ensemble cannot be realized just by guessing the most probable quantum sequence. Next, we consider following example 2. Example 2 shows that example 2 is that the factorizability of optimal efficiency discrimination does not generally work. In this example, from our result, we have this relation. This inequality is from theorem 3. This equality is from theorem 1. Thus, the factorizability of optimal average discrimination does not generally hold. Now, I will summarize. In this talk, we have considered multi-party quantum sequence discrimination and provide sufficient conditions for the factorizability of optimal average discrimination. And using these conditions, we show that the factorizability of optimal LOC discrimination is possible, but does not generally hold. Finally, I will discuss future work. The first question is whether the non-factorizability of optimal LOC discrimination occurs from the presence of entangled bonds. In other words, does there exist a separable quantum sequence ensemble for which optimal LOC discrimination is not factorizable? The second question is what measurement conditions allow the optimal discrimination of a quantum sequence ensemble can be factorized into that of each individual ensemble. Before I finish my talk quickly, because there will be a group of people lunch. As this is an important event, we would appreciate your participation. Thank you.